Today I'm going to be talking also about twisted bilayers, focusing mostly on bilayer graphene, but that's going to be my example. But the whole point will be this applies to more general systems. So I'm going to be talking about the electronic structure of mechanically relaxed, twisted, or incommensurate materials, and using momentum space. So as we already know, we can stack 2D materials, and they don't necessarily form a periodic structure, like this Gaim image shows, but can form an incommensurate structure where there is no true periodicity. If there is periodicity, then Bloch theory is usually applied, though if the system is incommensurate, then this breaks the periodicity, and other methods have to be used. Mitch already had a very nice introduction of configuration space, where you can use a real space type technique in order to compute electronic observables. Here we're going to focus on a momentum space technique, which is very related to K.P, where you use the plane wave basis, even though the system is incommensurate, and just understand how the incommensuration causes couplings between the waves. So this would be very similar to the work of McDonald and the Kixeris group also. And to put something else on top of it, to show the power of the technique, we're going to extend it to when there's mechanical relaxation. So we don't actually require there to be homogeneous, the two layers to be homogeneous. Here I'm showing just a twisted hexagonal lattice on top of a pair of lattices, so bilayer, without relaxation. And then after relaxation, you get these large domain patterns. So here you have AB versus BA stacking, you have domain walls, and then the AA stacked region. Here the mechanical relaxation is exaggerated, so it's easier to see. But usually the atoms relax slowly over time, over the distance. So I'm going to discuss how to use momentum space techniques and also incorporate that into when there is relaxation. Okay, so why do we want to do this? So real space type binding models are, there's a lot of development on real space type binding models, which gives a wide versatility of what kind of problems you can look at. You can have magnetic fields, twisted. If you can find the right type binding models, you could have defects. There's mechanical relaxation effects based off strain, like Sean was talking about. And there's a wide variety of problems. Momentum space is not quite so obvious from the get-go how to build the model, where to get your parameters. So that's a little harder. But if you do have a K.P model, if you do have a way of representing things in a plane wave basis, one, you get more physics out of it because you understand how the plane waves are interacting with each other. And two, it's usually a lot less expensive. Real space requires a lot larger systems. Momentum space usually requires much smaller systems, at least if the system is interesting in a plane wave basis. If you require a large system for a plane wave basis, then probably it's less interesting from a physical point of view as well. So it's a nice correlation of cost and physical insight. So what this work is going to do is build a framework to rigorously transform a real space model into a momentum space model. And as a particularly interesting example, we're going to do that for relaxed incommensurate bilayers. And we're going to show that observables, such as the density of states, are preserved under this transformation. So the transformation is an exact transformation that preserves all the observables that you're going to be interested in. I'm going to focus here on density of states, but we have work that also does this with conductivity. So we have that real space discussion of conductivity, but also a momentum space version for twisted bilayers. Okay, so to begin, I'm going to build on my framework on just a monolayer because that's a lot easier to understand. And also, what we have is a combination of monolayers end of the day. So this is going to build a framework for the rest of the analysis. So in a type binding model, I have for a monolayer, I have an underlying Bravais lattice, so a periodic lattice. I'm going to call that R. And then per lattice site, there will be a set of orbitals. So for example, in bilayer graphene, there will just be two PZ orbitals. So I'm going to call the index of orbitals A, and then my total degree of freedom space will be omega. So this describes my type binding degree of freedom space for a monolayer. And then I'm going to build a Hamiltonian that maps vectors over omega to vectors over omega. So that'll be my H. And I'll just describe that by this infinite matrix. And when I have a periodic system, this H is just periodic. So remember, R and R prime live on the lattice. So this R minus R prime also lives on the lattice. And H is just described by a function of the orbitals acting on the difference of the lattice. And then I'm further going to assume that there's an exponential localization Usually, actually used type binding model will just have a finite truncation anyway, so it will clearly satisfy this. Okay, so that's the real space model. And then to move to momentum space, in this case, it's just Bloch theory. So I'm going to call gamma star the reciprocal lattice unit cell, so that's highly related to the Brion zone. And I'm going to define my Bloch transform, G. This will be the key operator in this talk, which is going to move my real space psi into a momentum space. So here I'm mapping psi into this function over Q, where Q is my wave number. So this is a plot of just graphene's band structure. That's what happens when you're going to Bloch transform the graphene monolayer. So here we just have a standard Bloch transform. And then h psi in the case of the monolayer is just my little h convoluted with psi. As we all know, if we Bloch transform this, we just get gh, so the Bloch transform of h, times the Bloch transform of my vector. And here I'm just having this normalization constant to make sure g is unitary. And then what I can understand is that my new operator is now g star. So this is the Bloch transform of h. This operator is what I'm going to be interested in. And this is the exact kind of transform I'm going to apply to a bilayer, though the g will be a little bit more complicated in the bilayer case. In the monolayer case, it's pretty clear, it's just a Bloch transform. In the bilayer, it's going to be a little more complicated. And then, and then we know that the spectrum of h, which was a continuous spectrum in the real space case, will become a union of point spectrum over the reciprocal lattice unit cell. So standard Bloch theory. But we've moved from a large matrix where the spectrum is all continuous into a point spectrum where the matrices were very small. And so computationally much more effective, physically meaningful, because here we get the graphene direct cone. OK, so that's the monolayer. And now we can also describe observables like the density of states. So density of states will just be the normalized trace of the delta function acting on an energy. And so we can get a plot of the density of states from this. In the monolayer case, though, let's move this to a little bit smudged out of a framework. So we define it weakly by integrating the density against a small g, which will give us the matrix function, project onto a single site. Here I project onto a single site because the trace is just the sum of the diagonal elements of the matrix function. So here this matrix function, here it'll be gh. And since it's periodic, all of them are identical. So I can just project onto a single site of gh, and that will give me the density of states weakly. The reason I describe it weakly is because usually from a practical point of view, what you do is you convolute your density by a thin Gaussian, and that way you can actually get a plot of the density of states. We'll see that right here. So this is the sort of density of states plot you get. You take your density and then convolute it with a thin Gaussian, and you get something you can actually see. OK. Now what I want to do is transform that to momentum space into the Bloch basis. So this is another density of states formula you're probably all very familiar with. So here I'm just taking my real space version, which is the projection of the matrix function onto a single diagonal entry. And then I noticed that g star g is just the identity. And as a consequence, I'm just going to plug that in everywhere. So I'm just plugging in this identity operator everywhere, and I instantly transform into this momentum space. Here, this is an inner product between this function, and that's why I have an integral. And then just plugging that in, we have a density of states formula. So we go from a real space version, which was a projection of a matrix function onto a single site, into an integral over a smaller matrix. So we're going to want to do something similar in the bilayer case. Go from a large matrix trace, normalized, into some kind of integral over smaller matrices. These can be fully diagonalized. Here you can't. You have to use Chebyshev polynomials. OK, so that's monolayer. Bilayer, it's going to be the same thing. I'm going to have a lattice and orbitals per site. But now I'm going to label it by a sheet index j, because there's now multiple sheets, in this case just 2. So omega 1 union omega 2 will give me my total degree of freedom space, which I show a picture of here. And I just build my matrix, mapping omega to omega, vectors on omega to vectors on omega. And I can still make it as a function of the orbitals and the distance between the sites. But now R and R prime can live on different sheets. These kind of type binding models have been well modeled by Xiang and Stephen, and we can use these in our system. So we're just going to assume a form like this. Most of the models in the literature that are used for incommensurate bilayers right now satisfy this kind of condition. And we still have localization. So based off on your localization and so on, you get orbitals like this.
So why is that important to you? The exponential localization.
We want it highly localized because later on we're going to use Green's functions of h, and we want to use Coombs-Thomas exponential decay rates. So we want to know that because h is localized, the Green's function is localized, and that helps us make sure it's stable under the length scales when we move to momentum space. If you have long-range interactions, you could have some problems. Which, if there are real systems like that, that'd be interesting to play around with. So if you have ideas on that, happy to hear.
Okay.
Okay. And so we're going to assume that the system is incommensurate. So that means the two lattices are not periodic. The reciprocal lattices aren't, and the real space lattices aren't. OK, so we're in an incommensurate system. I'm going to briefly describe configuration, though actually I don't need it much. The only reason I'm going to introduce configuration is to understand what mechanical relaxation is. If you've already seen Paulstock, then you actually already know what's happening here. So first, configuration. So if I look at any lattice site, say on sheet 1, the blue site, I can parameterize where the whole local geometry by just where he is in the unit cell of the opposite sheet. So I have this vector b with respect to the unit cell, and this parameterizes all the local geometry. So if I want to understand relaxation, all I need to know is, given a lattice site, what's the vector b? And then I'm going to model, based off this displacement vector, what the relaxation is. So here I take a lattice site, and I just modulate by the opposite sheet, so it's always landing the unit cell, gamma 2 of the opposite sheet. OK, so U1 is going to be my displacement field. Because this is the displacement of lattice sites of sheet 1, I model it by where it lives in the opposite unit cell. So it's defined over gamma 2, the unit cell of the opposite sheet. Same for U2, the displacement of lattice sites of sheet 2. So I look at its configuration relative to where it lives in sheet 1. And so at the end of the day, what I do is I take a lattice site on sheet J, and I know its new position by just updating it based off of UJ. Okay, those should be not script arts. So it's just RJ mapping to RJ plus UJ RJ. This is the displacement of the site. So since this is just modeling all the displacement, these are some pictures of the relaxation and how some of the energy changes. For interest of time, since I have 20 minutes left, I don't want to go into too much of this, because I want to get to electronics of this guy. My new Hamiltonian is going to look something like this. It's going to be the coupling function plus the new distances of the site. Earlier, it was just a function of r minus r prime. Now I take it as a function of the distance of the new lattice positions, which is r plus the relaxed update, minus r prime minus the relaxed update of its sheet. So here I'm assuming r prime is living on sheet j, and r is living on sheet k.
And you're assuming it's the same function.
Right, I'm assuming it's the same function. So you can do some modeling updates if that's not true. The models we're using from Xerius group has this property. But if you know that other physics is relevant, then you need to play a bit more. For simplicity, we're not playing with that right now. One step at a time. If it becomes physically interesting, then it'd be fun to look at that. So again, if you have something. OK, so now I'm going to talk about the Bloch transform. So now that we're on a bilayer case, how do we transform to momentum space? We don't have the simple version in the monolayer where we just apply one Bloch operator and we're done. So the answer is we're going to take the Bloch operator sheet 1 plus the Bloch operator sheet 2, and that's going to be my total. I'm just going to apply the Bloch transform of sheet 1 to the component of the vector that lives on sheet 1, and the Bloch transform of sheet 2 onto the real space vector that exists on sheet 2. So here, the hats are going to represent the Bloch transform just acting on one sheet. Because I want to write my vector as the part that lives on sheet 1 and the sheet on sheet 2, I just define G1 as acting on this whole guy, and it's only the component that corresponds to the Bloch transform of sheet 1. So I have the sheet 1 Bloch transform, sheet 2 Bloch transform. This G is now my new Bloch transform for the bilayers, where I'm going to build all the K.P models, the momentum space systems. OK, so here I'm just going to let Pj be the projection onto sheet J, and I'm going to have Hij be the part of H that only describes the coupling of sheet I to sheet J. And what we find is we can Bloch transform our system by looking at each of these components. So here it's just homogeneous bilayer. There is no relaxation right now. I'm going to keep it simple and do homogeneous bilayer first. Here we just have standard Bloch theory. H11 is just sheet 1 interacting with sheet 1. So you're only interested in psi living on sheet 1. And then you're looking at the sheet 1 to sheet 1 interaction, so it's just standard Bloch theory. You just have G1H. Here we're doing sheet 2 on H22, so again, standard Bloch theory. It's just the Bloch theory of sheet 1 and Bloch theory of sheet 2. When I introduce the relaxation, actually this will not be so trivial because the phonons will cause scattering in plane from the sheet 1 to sheet 1 interaction and the sheet 2 to sheet 2 interaction. Here we have the interlayer coupling. So H12, this is where the scattering gets more interesting, and we have the interlayer coupling. The Fourier transform of the real space interlayer coupling defines the scattering. So here we have a wave number q coupling to a wave number q plus k, where k lives on the reciprocal lattice of the opposite sheet. So we took the sheet 1 Bloch transform, and because that will be periodic with respect to sheet 1, the sheet 2 reciprocal lattices show up in the scattering. If you are dealing with small twists, this will be a very small move in momentum space. So q will move to a very nearby q. Wave numbers will couple to nearby wave numbers. And so if you're looking at something like graphing, that means you'll stay within the Dirac cone as you start scattering around. Also, H12 was smooth and exponentially decaying, so H hat will also be smooth and exponentially decaying, which means that you are localized in the way these waves are scattering with each other. So that's going to be an important concept when we build the models. And actually a very interesting point when relaxation comes in, because this has become less local as relaxation effects come into play. You get less regularity, and so this becomes longer ranged, and you get more couplings. Okay, and these are just the required constants. Okay, another way of looking at that is just looking at the operator GH, G star. So this is just the Bloch transform operator. So H originally was just acting on real space to real space. GH, G star is now acting on functions to functions. So remember, it will be psi, where psi has a psi1 component and a psi2 component. Where psi1 is periodic with respect to sheet 1, psi2 is periodic with respect to sheet 2. Okay, so here we just have the standard Bloch theory terms. And then these are the scattering terms, where HK1, HK2 are just interlayer couplings. And what we see is we just have functions times translations, and then just the multiplication of functions. So these translations are just the scattering to nearby wave numbers. So this kind of operator is telling you that you're slowly scattering. And since we're only scattering with respect to specific periodicities, the R1 star and the R2 star, you can imagine this builds a lattice of reciprocal lattice sites. So if you fix your original wave number q, you're scattering to q plus R1 star with respect to the periodicity of sheet 2, and q plus R2 star with respect to the periodicity of sheet 1. So you're getting just a discrete set of wave numbers coupling together. And this means that we can move all of this to a lattice model, which is what we're going to do next. So now we are going to define H hat q, where we start with q. And now it's just going to be a coupling of reciprocal lattice sites. So we have a k alpha and a k prime alpha prime. Alpha is the orbital. K lives on a reciprocal lattice, and k prime lives on a reciprocal lattice. Here we're looking for interlayer, so that means k and k prime are on opposite reciprocal lattices. And the coupling of these guys will just be given by H hat alpha alpha prime, q plus k prime. So this is a coupling of q plus k to q plus k prime from a scattering point of view. Here is the intralayer terms. So as long as the k and k prime are the same, so here I just put k and k, then you just have the Bloch, just standard Bloch theory. But now because we've been moving along what wave numbers we're looking at, it's centered at q plus k. So we have the diagonal it's all Bloch diagonal, this whole operator H hat, but the Bloch diagonal entries change depending on what wave number you're looking at. So this term you could think of if you're looking at Dirac cone as you're slowly moving along the Dirac cone. Okay, and if we do the same thing we did with the monolayer, we do this transformation into the Bloch basis, we can show that the density of states is actually just this, what you expect. The G acting on your H hat, and then you just project onto the site and you integrate over the whole thing. So you're just integrating over your reciprocal lattice unit cell and integrating over your band structure, basically. So what do you expect for the density of states? Okay, so right now I've technically all described everything in terms of an infinite matrix. I have not shrunk this matrix at all, but as I advertised, we need to have a small matrix. And as already done in the physics literature, they use a very small matrix. And so to justify this, we look at this a bit more carefully. So I'm letting eta be my interlayer coupling strength. I look at the region near the energy of interest. Like, let's say I want to expand around the Dirac cone. I just look at the energy inside the interlayer coupling and look at what wave numbers those correspond to. So that forms these little red dots here. And then what I'm going to do is just add a buffer region to this. So I'm just looking at wave numbers, and I want to know what wave numbers are interesting. I add a buffer, so I see if you can see it, there's a little red dot in the center, not my pointer. And then there's a dark region around it, which is my buffer region, which will control my error. So I just add some buffer. That's probably a lot more buffer than I need. And these are the wave numbers I'm going to consider strongly coupled. We do some rigorous derivations that these are the wave numbers that we care about. But for the interest of time, I'm not going to go into that too much. Now, every lattice site, this is the two reciprocal lattices, every lattice site had an associated wave number. So if I started with Q, then it was Q plus K, depending on which sheet you're in. So if I know that these are the only wave numbers that are coupled in an interesting way, I'm just going to map this set of wave numbers to the reciprocal lattice sites that are of interest. That technically is an infinite number, but what you can see, and this is bilayer graphing, by the way, these are two Dirac points, is that they're all isolated regions. And some of these are going to be very repetitive of each other. So let's take the two Dirac cones, say K and K prime. I'm going to be interested in only in these two. And these are actually separate calculations, because these guys are not talking to each other. These are the only reciprocal lattice sites that will contribute strongly. And so I just isolate these, and I can do my whole density states calculation with this subset of degrees of freedom. Those are the only ones I need. OK, and so from that, OK, so we have, because of this, we have an h hat q that's now a lot smaller as a function of q. I can plug that in here, integrate over a small region in q, and that will give me the whole density of states. But this also gives me band structure, because now I have a very small h hat q. So this is if you do the k dot p expansions, this is the equivalent. You get a small h hat q, and you can just plot the eigenvalues directly, which will tell you a lot of physics. So here is an example of some band structure you can get from this. And this is just the two cones talking near each other, and here you have the level sets of this energy for different angles, here without coupling and with coupling, without coupling, with coupling. OK, so that's the framework. And then the thing we want to add is mechanical relaxation. OK, so if we want to add mechanical relaxation, all right, so first I'm going to pretend that there's no interlayer coupling, but I will get to interlayer coupling. It's important. So what I basically want to do is take my HU, and I want to do G, HU, G star. Because that HU is just my real space Hamiltonian with relaxation. I want to Bloch transform it using the Bloch transform that Bloch transforms sheet by sheet. And I want to get a new guy. So let's take a look at what my guy looks like. And for now, I'm going to ignore interlayer coupling, because interlayer is so easy. So I'd like to just start with the easy thing and then add the harder part on afterward. So I actually can realize, based off of what this was, remember, r minus r prime, this was r, and this was a minus r prime here, or an r prime here. I can actually just write a new interlayer coupling function that's still just a function of x, or the r minus r prime. I'm not going to derive that for space reasons, but this describes the coupling from sheet 2 to sheet 1. And as a consequence, this still has a Fourier transform, which means all of the Bloch transform I described earlier still applies in this setting. What are U1 and U2 are the relaxation functions. So U1, U1 is how much sheet 1 relaxes. So it's a function over the unit cell. And so if I plug in a lattice, actually, let me just jump back to where I defined it. Sorry, it was a little earlier in the talk. OK, so these are the relaxation functions. If I have a lattice site rj, sorry about the script, it shouldn't be script, it moves to rj plus uj rj. So this is you can think of it as a periodic extension of this guy. And what I do is I input my lattice site. It modulates by the opposite periodicity, which gives me configuration. And then this tells me how much the atom moves. So if it landed here, which is near an AA site, he starts moving to an AB site, for example, because he likes to be in a low energy AB configuration, which gives you these large domain patterns. So originally, this looked not nearly as nice, but they all move to positions they like, AB or BA.
The U's are prescribed?
The U's here I'm just giving, but that would be derived by a different model, like the one Paul was talking about. But there's an elastic model for describing mechanical relaxation, which is a completely separate calculation than the electronic. So we use two separate models, and I'm inputting a model here. Yeah, good question. OK, so if I have these relaxation functions, this is my new interlayer coupling. I can Fourier transform that to get the coupling. So here, I'm plotting just real space coupling without relaxation. If I include relaxation, I get a coupling like this. This is because of these sharp domain walls and boundaries in the A regions that you get this triangular patterns in there. And then if I Fourier transform this guy to get the interlayer coupling in momentum space, I get something like this. It's a nice localized guy. Hopefully it shows up, well, it shows up some here. If I move this guy to momentum space, you see he's a lot less localized. There's still strongest sites here, but you can see that there's now expanding out regions. The image isn't perfect on this projector, but this actually keeps going out in the hexagonal line directions. And that's going to get, those features get stronger and stronger depending on how small the twist angle is. Smaller twist angle, the stronger those features, because these domain walls are sharper, which means the Fourier transform is longer ranged. OK, and so then we have our relaxation function, and now I want to move the intralayer coupling. So to do intralayer coupling, he doesn't quite work to Bloch transform this guy. So what I do is an approximation. You can do higher order approximations than this, but I'm just going to do first order. I can just look at what this relaxation function is. And it actually turns out UJR and UJR prime are actually very close to each other. As a consequence, I can Taylor expand this guy, and I just get some terms like this. This guy now I can Bloch transform. Not in a standard Bloch theory, there will be scattering, but it will actually give me something meaningful. So R and R prime, because I'm on intralayer, on the same lattice. So this guy's periodic, this guy's periodic, this guy's periodic. So the only guy that's actually breaking periodicity is this guy. And that's the one who's going to generate scattering. Notice that UJ has the opposite sheet's periodicity. So it's not got sheet J periodicity, it's periodic on the opposite sheet. And these are just, this guy just scales as the inverse Morley length scale. So he's small. That's what's making this term perturbative, which allowed me to do Taylor expansion. OK, I'm just going to define P1 to be the equal 2 and P2 equal 1, so I can look at opposite sheets. So to actually address this guy, I'm just going to Fourier expand UJ, which is going to give me Fourier terms here for just UJ, and then this is for the derivatives of UJ, because I had a gradient up on the last slide. And so I can rewrite this in terms of the Fourier modes. And then this guy, it's a quick calculation to Fourier transform to apply the Bloch transformations. And that keeps me on this, the two reciprocal lattices are still interacting. So I have the same degree of freedom space. It's reciprocal lattices on sheet 1 interacting with reciprocal lattices on sheet 2. Which gives me interlayer coupling, or interlayer, sorry, and then intralayer. So here we just had the Bloch term. This is the effect from the phonons, the in-plane interactions. This is interlayer. And I'm wrapping up here. So then here we have the flat band, where originally this is without relaxation. And then if we include relaxation, you see that these gaps widen and the effects change quite a bit. And so that's the completion of my talk. We just moved, to summarize, we moved from real space to momentum space. And we can include mechanical relaxations. This is a general framework for doing the Bloch transform into a K.P type framework. Thank you for your attention, and thanks for the invite.